Right. I made a mistake yesterday when I said that a group element of this form, if you take the derivative of this, you get this. That's not true, because this matrix element and this matrix, so this matrix and this matrix are different matrix and they don't commute necessarily. And a lot of the confusion in the formula I wrote out after that stem from that mistake. So I'm not going to prove it, but it is possible to show that the G inverse dG that I wrote down, it is a Lie algebra valued object. So it is in the cotangent space of the manifold, and in the Lie algebra of the group and the Lie algebra. Now, morally speaking, the Lie algebra is something that is, that is related to the tangent space. But just because this thing lives in the tensor product of the cotangent space and the Lie algebra doesn't mean that we are taking the inner product of those two guys, right? Because we can always have, for example, if you have a tensor in general relativity which has a covariant and a contravariant index, right? That object lives in T star of M cross T of M, but this is not an inner product. And I just wanted to kind of, the expression I wrote down for the metric was just something that I just wanted to flash without having gone through it in any rigorous way. But I just wanted to clear up the confusion because I did make a mistake yesterday. Okay. So we were doing SU2 tensors yesterday, and we'll try to get into SU3 today, but I don't think we'll do justice to SU3, which is unfortunate because you will come across SU3 more, although not in a very mathematical context in particle physics. But we want to build up towards doing the Young tableaus today, okay? So we want to see how, given the different representations of SUN, how we can how the product of those decomposes into sums, and how to do that sum. Basically, how the generalization of the Clebsch-Gordon series works for SUN. So let's start back with SU2 again. And we said that, like this thing where A is 1 and 2, this thing is in the fundamental representation of SU2, and the complex conjugate, which I wrote as this, is in the anti-fundamental, but the fundamental and the anti-fundamental in SU2 can be related. And we also introduced some invariant tensors for SU2. These are invariant under SU2 transformations. Right. So now, using these invariant tensors, suppose I have a fundamental representation of SU2. Of course, and we are kind of ignoring, although these are the same thing, but for a lot of the properties generalized to higher to SUN, SU3 and higher SUNs, if you ignore this fact, a lot of the mathematical properties generalize. So for example, given like a fundamental of SU2, I can ask the question, say, what is this object? How does this object transform? We know that this object transform as u of AB psi of B. Now, you can show that, well, now if I make the transformation of this guy, then I should get, because it has upstairs index here, so the upstairs indices should transform in this way, B prime U dagger of, say, A prime A, and then this has downstairs index, so this should be, say, A C psi of C, right? But then we see that, you know, these two guys have this index A common, and this this matrix is the inverse of this matrix. So I can replace this with A prime C. Sorry, bad blackboard technique here. And then I can see that, okay, this thing then becomes U dagger of B prime of B delta A prime C psi of C, and then this becomes U dagger B prime. I made some mistake, I'm sure.
B and the B prime is supposed to be the other way.
Sorry?
B and the B prime? Yes.
Oh, right. So this should be, when I take this into account.
There's an epsilon missing.
Oh, yeah, of course. Yeah. Sorry, I'm a bit slow today. There should be an epsilon, and with B prime and A prime, right? And so let's get, yeah, B prime, A prime. Okay, good. And so if I do this, then this A prime makes it into a C. So I get U dagger B prime B, and this thing is B prime of C, and this is C. So if I define this object to be, say, chi of B, then this becomes U dagger of B prime B chi of B. Sorry, B prime, right?
Shouldn't that be psi A prime after you apply the delta?
Psi.
You summed over the A prime of the C.
Did I make a mistake here?
Oh, sorry.
Yeah, no, anyway, I mean, don't worry about it. I mean, we all make mistakes. So what I'm trying to say here is that using this invariant tensor, when we contract it with some other tensor, it transforms a 2 into 2 star. Okay? So so the moral of the story is that if this is if this is a in 2, then this object is in 2 star. I'm of course ignoring the fact that these two things are essentially the same here in case of SU2, but we'll see in the SU3 these things are not the same. So I mean, this is an example of a tensor which is irreducible, but tensors with more indices won't necessarily be irreducible. And let's take an example. Suppose we have a tensor with 2 indices, an SU2 tensor. This is an SU2 tensor with 2 indices. Then I can write this as an antisymmetrized version and a symmetrized version. And then you can check that you can check that under under SU2, this thing and this thing don't mix. And although I'm not going to prove this fact, they actually form irreducible representations. So suppose I give you a tensor, a general tensor, and I tell you, so this is not going to be irreducible. So a general tensor, not in general irreducible. A strategy of constructing irreducible representations would be symmetrizing them and anti-symmetrizing the indices. So here all the indices are downstairs, but you can also have a tensor where an index is downstairs and an index is upstairs, or for example, you can have things like this. Now this is not irreducible because a SU2 transformation doesn't mix with this, but you can then contract these two guys. So you can say you can take this and contract it with, and then you see that this thing will transform as a singlet. So let's do some examples. Did I introduce Young Tableau yesterday? Yesterday was a blur for other reasons. So let's take some examples. So take a rank 2 tensor of this form. So something like this, where this is, this is a 2 and this is a 2, which is different, independent. We can write that as 2 tensored with 2. Now, this thing we can now say, we can express as an antisymmetric part and a symmetric part. Now A and B goes from 1 to 2, so this thing will have only one component. So this is going to be 1. And this thing will have 3 components. So this is 3. So the 2 cross 2 breaks up into 1 plus 3. And this from quantum mechanics, where if you combine 2 spin half particles, you get a vector representation and a scalar representation.
Sorry.
Yeah?
What's a singlet? I've never seen that word used before. It looks like a scalar, but
It is a scalar, yeah.
So they mean exactly.
Yeah, a singlet is something which doesn't have a free SU2 index. And under an SU2 transformation, it doesn't change. Whereas, for example, a fundamental, this object under SU2 transformation comes with some. Okay, so this is, yeah?
Should the indices be the same on the left of that arrow? Like chi A, psi B, should they be both A's or both B's?
Here?
Yeah.
For the singlet?
No.
For the singlet thing, yeah.
Yeah, this is a singlet.
So
because I've contracted those things.
Shouldn't it be
there's three indices there, which
Side.
is
Right. So okay. Yeah. Exactly. Yeah. No. So what I'm saying is that suppose I have a 2 times 2, and I want to construct a 1, then I'm the so sloppy notation. Thank you very much. So that's why. Then how do you construct a singlet from a 2 plus 2? You take the Kronecker delta, the invariant tensor, and you contract it. You use that to contract these indices. Okay.
okay.
This means that the 2 times 2 is going to come down to singlet plus something else. And I'm going to single out the singlet part, or what?
Right. I mean, the thing is that we are so 2 plus 2. This is some, this is some vector space. I'm projecting down to a subspace of the vector space, which is the singlet space, and that's how the delta is being used. The delta is being used to project down. Okay.
So the arrow wasn't like a transformation.
Yeah. Sorry. So.
It's 2 times 2 star.
Sorry.
It's 2 times 2 star.
Yeah. And thank you, because that's very important. Because of course, for SU2 they're the same, but for SU3 they won't be the same. So that's very important. Thank you. Okay, so let's just play a game where we say that if we have so I'm going to introduce some young tableau along the way. So we say that if we have a fundamental, we write it like 2, but we represent this as a box with the index inside the box. When it's, at some point we are going to drop those indices inside the box, but for now we keep it. And if we have some rank 2 tensor with 2 indices which are antisymmetrized, now how many components are there in principle here? Sorry? 1. Because then that's going to be 1. And for antisymmetrized rank 2 tensor with 2 indices, I'm going to do 2 boxes, and I'm going to put the boxes on top of each other. So whenever I put boxes on top of each other, that means that I am referring to a tensor whose indices have been antisymmetrized. Similarly, if I have a rank 2 tensor whose indices are symmetrized, so for SU2, what is the dimension of that? 3. And how do you think we should represent this? Right. So that statement, 2 times 2 is equals to 1 plus 3. 2 times 2 is equals to 1 plus 3. In this box language can be written as so note that for SU2, something like this cannot exist, because that means you're antisymmetrizing 3 indices, but each index takes only the value 1 and 2, so that would be 0. So next, let's do a very instructive exercise. Let's figure out what is 2 times 2 times 2. What is it? So, so basically, I'm developing some basic intuition for the Young tableau, and I won't derive the whole thing, but basically, I'll be switching between tensors and Young tableau. Basically, I'll be using tensors because it's easy to see explicitly, but the Young tableau will come as a way of encoding the results. Okay. So we want to know what this is. Okay. So we can write this as right. Now we already know what the first part is. This is a sum, so I can write. Okay. Now, this is a singlet. So the third, fundamental representation, multiplying this should just give me this, because this is just a 1. This is just some scalar multiplying a fundamental. So the non-trivial part, should come from this thing. Now, what is this? So to see what this is, it's good to actually switch to tensor notation. So this is a symmetric tensor. I'm just going to put 3 for 3 times a symmetric tensor. I'm taking some symmetric tensor. It doesn't matter exactly what symmetric tensor you take, but I'm taking one that's convenient, that's made out of some fundamental stuff. So this is basically what this object is. Now I will write this as this. Let's see if I. Okay, right. And the first term is the same for all these guys. Here I subtract this thing, which I added, and then I subtract that guy. Okay, so now you can expand the first line. So we can expand the first line. And what we find is something with 3 terms. Okay?
So your phi on the second line, should it be phi psi?
Yes. Right. Right. Oh, sorry. Thank you. I find 6 terms, and do you want me to write it out? So this is phi psi c chi b phi a psi c chi b phi c psi a chi c phi b psi a chi c phi a psi b chi a phi c psi b. Okay, so this is completely symmetric in A, B, and C. Okay. So this is symmetric in A, B, C. So it has how many components? In SU2?
Ah, okay, yeah.
Out with it?
3.
4. And why? So if you have a symmetric tensor in SU2, sorry, did I say SU3? SU2, right? Then this will always be n+1 dimensional for SU2. And that's because one of these, 0 of this index can take the value 1, or one of them take the value 1, or 2 of them can take the value 1, up to n. And everything else is related by symmetry. Okay, so this is always going to be. So this will be 4-dimensional. Okay, what is the second line? The second line is now see that this term and this term, these guys are common, but these two terms are antisymmetric in A and C. In this term and this term, this guy is in common. It's also antisymmetric in A and C. So we have something that is antisymmetric in A and C. And then if you now expand the third line, you find that that is exactly the same tensor as this tensor. So you don't actually get anything new. You get a different tensor, of course, but the indices are different. The label of the indices are different. So then what we can do is that we can take this guy, which is antisymmetric, in C and A, and contract it with epsilon C and A. See, I mean, if you contract it with epsilon C and A, we are not losing any information because it's already antisymmetric in C and A. So I contracted with epsilon C and A, CA. Then the free index left is B, which I call this an eta B. So this shows that this object is A2. And then, therefore, we can write that Now you might say that, hang on, this is very confusing. You write some box thingy which has 3 boxes, and you say it's 4-dimensional. How the hell am I supposed to memorize that? You know, so but at the end, when I actually, after motivating with some examples, I will come to the formal rules of Young tableau, and I will give you the algorithm for computing the dimension of the representation that corresponds to a Young tableau for SUN. Okay? I'm just kind of building this thing up right now. Okay.
Sorry.
Yeah.
I'm just confused. Like, to get the eta b, you have to contract with an epsilon. That wasn't part of your original tensor.
No, it's not part of my original tensor. You're right. Yeah.
So why? I mean.
Very good. No, that's fine. So what I'm saying is that, you know, suppose you have some object which is, say, what do you want to call it? A, which is, say, 3 indices. It's an object which doesn't have any obvious symmetry. Say it is CAB, but it is antisymmetric in the first 2 indices. Okay?
Wait, what's that?
Oh, sorry, ACB, right? Yeah, yeah.
Like ACAB is equal to minus ACB.
The minus.
Sorry. Sorry, my brain is a bit slow today. Right? So, so now, I mean, if I now compute how many components it has, it can have, say, 1. The first index can be 1, right? And the second index can be 2. And the third index can be either 1 or 2. So it can be 1, 2, 2. Now, the first index can also be 2. Okay, the first index can also be 2, but because it's antisymmetric, the second index must be 1. And the third index can be 1 or 2. And similarly, 1, 2, 1, right?
2, 1, 2.
Sorry, yeah. So, this is 2. This is 1.
2, 1, 2.
2, 1, 2.
Yeah, 2, 1, 2. Yeah, yeah. Sorry. So now you can ask, you know, how many of these guys are actually independent, right? Well, we have 2, 1, 2, but that's just the negative of 1, 2, 1. And we have 2, 1, 1, but that's just the negative of 1, 2, 1, right? So this thing has actually only 2 independent components. So it is more efficient for me to write this as something which has only 2 independent components. And so I could have just written it like the way it is, but if I contract it, because the antisymmetric indices, if I contract it with the epsilon tensor, it kind of shows clearly what I'm dealing with. Okay? So,
You're always just counting the number of independent.
yeah, exactly. Yeah, yeah. All right, so so again, something I said before, but let me reiterate for SU2. This thing will always be n plus 1. So now that we figured it out, we can answer that question over there. What is 2 times 2 times 2? Well, 2 times 2 times 2 is 4 plus 2, and there was a 2 coming from before. So let's move on to SU3 tensors now. Tomorrow we'll talk about SU4 tensor. I'm just kidding, yeah.
So in the top right on the
Yeah.
top board, when we wrote out like 3 chi phi psi, we got these 3 lines.
Right.
We said that the first line was a copy of 4, and the second line was a copy of 2. Why don't we get an extra copy of 2 from the third line?
So the third line, so if you write it out again like this,
Yeah.
and you contract it, you get exactly the same. You get the same tensor.
So why don't we get an extra copy of that tensor?
Yeah, those two live in the same vector space, so they add up. Yeah. If you were getting like a different combination of these guys, which was also 2, that would be a separate 2.
In that case, it'll be antisymmetric between like B and C instead of A and C, right?
Yeah, but they're just indices, so they're just yeah. So for SU3, we have the fundamental. So this is the fundamental. And 3 star, which is the anti-fundamental. For SU3, the generators that you get from doing a complex conjugation, these are not related to this by a similarity transformation. So no C's such that TA tilde is C TA C inverse, unlike SU2. So we can then say, what are the invariant tensors? These are the 3-dimensional, the Levi-Civita with the 3 indices, and again, delta AB. Now let's consider phi AB, where a tensor with antisymmetric indices. So how many components does it have in 3 dimension for SU3? 3, right? So we might say, okay, what kind of object is this? Is it a 3 or 3 star? What do you think it would be? It should be 3. Any other? Well, the other option is to be 3 star, right? And remember that over here we showed that for SU2, if you have something like this, which was a 2, when we contracted it with an epsilon, this whole thing became a 2 star, right? You can do exactly the same thing with this guy and take an epsilon and okay, let me just write this separately. So by contracting with an epsilon A, B, C, you can show that this thing is a 3 star. So in other words, I can define, say, something with an upstairs index and this is going to be a 3 star. So something like this is going to be a 3 star. So this motivates that we express the 3 as box as before, and that's because it's going to be something like this. But the 3 star, this is something like this. So you can invent a notation where you write the box above the box, or you can use the fact that something like this can actually be related to something where the indices have been antisymmetrized, and then say that this is actually going to be something like this. Yeah?
How do you know when you contract the first tensor with the antisymmetric tensor that you get something that's the same object?
Sorry, which one?
So how do you know when you contract phi antisymmetric BC with the epsilon that you get something that's the same object as phi BC?
Same object?
How it transforms.
How it transforms? Okay, I mean, we can do this. So if I take this, right, and let's see how it transforms, right? Then, we have ABC, phi of BC, and if I transform, it's going to have 5 unitary matrices. 3 of them will be U daggers coming from this guy. 2 of them will be U's coming from these guys, and of those 2 from U daggers will get rid of the U's coming from here. What you left behind is a U dagger, and that's how.
Yeah.
All right. So remember that for SU2, this thing was a 1, right? Because for SU2, you have 2 indices. If you antisymmetrize something with 2 values, the index can take 2 values. When you antisymmetrize an object with 2 indices which takes 2 values, you have only 1 component. But in this case, that's not the case. So can someone guess what would be the singlet of SU3? How many boxes should I write? 3 boxes in a column. So that should be this thing, right? All right, let's do some examples of SU3. Okay. Examples. What is this? So we take some tensor and So for SU3, this has, as we just saw, it's three components. So this has how many? 6. So this has 3 components. So I write it like that. And the 6th component is this. Remember, for SU2, this had 3 components. And this I write as 3 times 3. But as we learned, this is actually 3 star. And this is a 6. So let's do another one where we, instead of 3, we say 3 star. And let's increase the stakes a little bit. And we say that psi A now is an up quark, a down quark, and a strange quark. So what we are doing is that we are taking a fundamental of, a triplet of quarks, and 3 star is then the anti-quarks. Okay? So you will find that when you do Standard Model and QFT that, the anti-quarks, antiparticles, they belong to the conjugate representation. So just keep this in mind, and then what we will find here are essentially the mesons that are formed by quark anti-quark pairs. Right? Okay, so now so this thing can be expressed as, let's use psi b. So this is my box times this thing. So if I contract this thing, I actually get a singlet. Right? So it turns out that that's the only thing I can do. The singlet transforms trivially, so that is obviously a irreducible representation, trivial but irreducible. But this you can't really reduce anymore. So what we do is that we take the trace. We take the trace out of this guy. So we take so this is a 8-dimensional representation, and this is the one-dimensional representation.
I think the second term with the delta should be AP.
Second, this one?
Yes, because delta, you're contracting delta AB with C's, right?
No, I've already contracted CC. I'm just putting this delta so that this term and this term transform in the same way. And so to see that this part, it is actually So how do you represent the 8 as in terms of Young tableau? I'm going to claim that the 8 is represented in this way. And so this won't be very, this would be a bit heuristic, but I hope you bear with me. And the way to see it is to kind of see that, okay, we have some psi A and some psi B, but the psi B can be written as, okay, sorry, it's actually easier if I write the psi B first. Okay, write this. If I do this, now this is in the 3 star, which means that I can write this as, say, B, C, D of some object which is antisymmetric in C and D, and like this. So, however, this thing I can call, it's this object, and this is some box. So the important thing here is that if I look at this part within the brackets, it is antisymmetrized in these indices, but it's actually not symmetrized in these indices. And that's something we'll see that in Young tableaus where we have, which is kind of not a pure column or a pure row, the indices along the column will be antisymmetrized, whereas the indices along the row will not necessarily be symmetrized. So this basically tells us that this thing will be for can read Jones for slightly more details. Now, we can now look at this more carefully. So, or what I mean is that I can now take these guys, plug them in, and work out what the matrix element, what the different components of this tensor is. Because it's a rank 2 tensor, you can actually represent that as a matrix. And it turns out that they form the entries of this rank 2 tensors are different mesons that are found in the physics of strong interaction. So if I call that tensor, say P of AB is psi A, psi B third. Then it turns out that this is some pi naught. So you can look up their core contents. I won't write them down here. But these are the wave functions of the mesons. So that's a historical application of 3 times 3 star. You can also say, okay, what if I take 3 quarks and multiply them together, 3 fundamental representations of SU3? You should get, for example, the neutron. You should get a proton, and you should get a bunch of other stuff. And so it's physically interesting to ask, what is this? I'm not going to derive this right now. Maybe something we can do in this tutorial today. But this is some, I'm just going to give you the result. And here you get 2 different 8s. And this is the 10. This is 8. The 10 is very famous because it contained a state that has not been observed when this was predicted. And using, so of course the up-down quark, up-down and strange quark, they don't have the same mass. They are kind of approximately the same, but using quantum mechanics and some heuristic argument, you can predict their masses to certain accuracy. And it's only after Gelman, worked this out and showed that there should be this 10th particle, which he called omega, it was actually discovered. So this group theory of SU3, all this tensor analysis, it's really put quark on the map. Well, basically that's how we discovered quark. I mean, there were even after that, people were talking about whether quarks actually exist or not. And then, I think in high energy physics, there's actually evidence that quark exists. So now, wouldn't it be nice to have an algorithm for generating this series instead of doing this painful tensor manipulation? Because the tensor manipulation, it seems like you're just pulling stuff out of thin air sometimes. You have to guess, oh, this is how. And that's really formalized in the Young tableau. So I'm going to give you now the rules for Young tableau. I've just motivated where Young tableaus come from. Now I'm just going to give you how to compute the dimension of Young tableau, how to work out the Clebsch-Gordon series and stuff like that. And I don't think I shall get to SU3. So these are Young's table. So first, illegal. And this is taken from Jones. So if you want to read in more details, you can look at Jones. A legal Young's tableau okay. So in a legal Young tableau, the length of any row cannot be larger than the row above. And we stack the Young tableau such that we align them on the left. So a Young tableau should look something like this, one that is allowed, i.e. legal. If you draw a Young tableau which is not legal, the tableau police will come and put you in a jail, whose bars are made out of legal Young tableaus. Sorry for that bad joke. So what is not allowed is stuff like that. So this is not allowed because this thing is longer than this thing. This is allowed. So the number of boxes in a column for SUN cannot be more than n due to antisymmetry. So if this was, say, SU, this could not be SU3 because the tensor that this Young tableau would represent would have 4 indices which are antisymmetrized, and for SU3, that would give you 0. So later we shall see how to build up the Krebs-Gordon series from a given initial set of representations. But for now, suppose we have a Young tableau with n boxes. So this is number 3. Suppose we have a Young's tableau with corresponding to a rank n tensor. So okay, that's not the right way of putting it, sorry. Okay. Suppose we have a Young tableau with n boxes. Say, okay, with n boxes, And we have a rank n tensor from which we have to construct this representation. Construct the irreduced representation corresponding to the tableau. Then we do something like this. What do we do? What we do is that let's take a particular example. Suppose this is the tableau that we have. So it is some erep So this has got how many boxes? 1, 2, 3, 4, 5, 6, 7, 8. And we are told that this erep arises from doing some kind of projection on some tensor which has 8 indices. How do we go about that? So what we do is that starting from left to right here and left to right here, we fill out these boxes with the indices. And then what we do is that we symmetrize first. And then 3A, we first symmetrize along, symmetrize the indices which lie on each row. So here we have 1, 2, 3, 4. So what we say is that, okay, I'm going to take this and then I'm going to symmetrize A1, A2, A3, A4, and then I'm going to symmetrize A5, A6, A7, A5, A6, A7, and then I'm going to symmetrize A8, which of course means because it's only one index, I don't have to do anything. So once we have done that, we have to symmetrize, anti-symmetrize the column. Then we anti-symmetrize the columns. So basically now we have A1, A5, A8. So we make, if you like, we take this guy and we say, let's take, well, this doesn't have to be SU3. So yeah, that you have to anti-symmetrize these 3 indices, and then anti-symmetrize these 2 indices, these 2 indices, and this. Again, A4 you don't have to anti-symmetrize because it's by itself. The net effect is that the symmetrization that you did first gets lost. That symmetrization is the anti-symmetrization tells you that, means that this indices may no longer be symmetrized. The symmetrization that you did initially, some of it will be kind of, ruined by the anti-symmetrization process, okay? And so once you have anti-symmetrized this, so, then you then you can be assured that the resulting tensor you get will correspond to the Young tableau that you drew down. Now, suppose I give you a Young tableau and say, okay, what is the dimensionality of this Young tableau? Yeah.
So the symmetrization, for example, says if you switch A1 and A2, then you still get the same tensor. And the anti-symmetrization says if you switch A1 and A5, you get the
Minus of that.
So aren't those kind of independent of each other? Like, you never have two indices which are simultaneously in the same row and same column, right?
Yes.
So you can have both A and B exist simultaneously.
And then how would the symmetrization get lost?
How this? I think, yeah. I mean, so you're right. So if I was doing only one anti-symmetrization, it wouldn't get lost. But I'm doing more than one in principle. And then, so for example, this thing will basically now A2 and A6 would be anti-symmetrized. And then, so that would actually ruin the symmetrization of A1 and A2. But if it was just one, it wouldn't. I think you have to really do some explicit calculations to see that.
But is it true that if you do just one, that it wouldn't be ruined? Because I think for like SU2,
that's my guess.
One, I think it would be ruined too.
No, it would be ruined. Yes, yeah, you're right. Yeah, sorry. Yeah, that's a very good point. So yeah, we did do an example where we did the 3-index SU2, and we wrote it as a symmetric, and right. So this was something like this, right? And in that case, this was anti-symmetrized, whereas this wasn't, right? Yeah, exactly. That's a good example. Okay, how do we? The other thing too that is interesting that I'm, I don't really know how to prove this, but I read about it in Jones. But I think it's worth mentioning is that the Young tableaus form irreducible representation of the permutation. And that's an interesting observation. That somebody in some math course will prove. So how do we compute the dimensionality? So that's point number 4 is how to compute the dimension of a tableau. So let's take a tableau for example, and let's take this to be SUN, because you have to commit to a particular group. And then we form a quotient like this. So basically, I'll get two numbers, and I'll have to form the quotient of these two numbers. And on the left top corner, I write, for SU1, I write n here. And as I go down, I decrease by 1. So this is n minus 1. This is n minus 2. This is n minus 3. As I go right, I increase by 1. So this is n plus 1. This is n plus 2. As I go down here, I decrease by 1. n minus 1. And here in each box, I look at the right and the below. How many boxes are there on the right and how many boxes are there below? How many boxes are there on the right? And I write, and they add 1 for this box. So here it should be 1, right? So how many boxes, what should I put in this box? 1. Because there's 1 box on the right, no box on the right, no box on the below. How many boxes on the right? 1. 1 below. So I should write 3. What about this one? What should I write here? What about this one? What should I write here? Boxes, not the numbers. 1, 2, 3, and 4 for the box itself, right? Right. And this should be 1. This should be 4. And 1, 2, 3, 4, 5, 6. Right. So let's do for SU3. Now let's do this for SU3. Sorry.
We still didn't get the dimension.
Sorry?
We still didn't get the dimension of the first one.
Yeah, that's, basically when you do this, I'm going to show how this works.
You have to multiply something I forgot about.
Yeah. So this would be the dimension. Like you have to write, basically these numbers. You have to write the product of all these numbers divided by the product of all these numbers, and do that, and that's it. So for SU3, it's easy to see that this is going to, this guy is going to give me is 3, 2, 4 divided by 1, 2, 1. So in the numerator, I have 3, 4, 2. In the denominator, I have 3. So I have 8. So the last thing is how to expand given, suppose I give you, yeah?
Yeah, how did you calculate the dimension here?
Okay, so I'm doing SU3 here, right? So I say, okay, I'm going to write 3 here. And as I go down, I'm going to decrease. So I get 2 here. As I go right, I'm going to increase. So I have 4 here. And over here, on the denominator, I say, okay, how many boxes are below this?
I understand how you fill in the boxes. I just don't understand the computation you just did.
Oh, okay, right. So then what we say is that this is the numerator. So in the numerator, we have 3. We have 4 times 2. In the denominator, we have 3 times 1 times 1. And we work out what that is. And that should be the dimension, okay?
Okay.
Yeah?
Are you sure it's just the multiplication of numbers? Because I remember learning something about certain rules that some columns go with some rows and then you add some.
Maybe that's for
Maybe. I mean, I've seen this being described in different ways in different books.
Could that be for things other than SUN, maybe?
Could be.
So I mean,
Time goes.
no, I mean, I'm giving it the most basic thing. I mean, I think there are probably, other ways of describing the same thing, like hooks and stuff like that, and those kind of things.
You're thinking about how they're, like, when you have two of them, how you multiply them, how you add the boxes one to the other?
Anyway,
Later.
yeah, I mean, this is, different people describe it differently, and I'm sure it's possible. Okay, so the last thing is how to expand the Krebs-Gordon series. So suppose we are given two boxes. How do we expand them in terms of irreducible representation? And this is really probably going to be the toughest to explain. So how to expand the product of two tableau as a sum of tableaus. So we have, for definiteness, let's take something like this. So this is T1, and we're multiplying with this T2. So the first rule is so label the rows of T2 by A for the first row, so B for the second row, C for the third row. You get the idea. So I have, so this is A, this is A, this is B, this is B. Second is add one box from T2 to T1 at a time, such that at a time, starting from the top row. So making sure at each step the following are satisfied. The following rules are that T1 must be, so okay, you start from the top row and then you work down. Okay, so you start with this row, you take this guy, and then you work down. And so at each step you have to ensure that T1 must be a legal Young tableau at each stage. Maybe I should not call it T1, but the first tableau. Okay, make sure. I think what I mean is that at each stage, right. So I think it's each tableau must be a legal Young tableau. So more than one box with the same label A, for example, same label must not appear in the same column So for each box, assign a number, number, say n of A, which is the number of A's above and write to it similarly assign B, similarly assign a number NB in the same way. And if that box, and that box in the end, the number of A's, NA must be equal or greater than NB must be equal to NC. If that is the case, then you're allowed, that tableau is allowed. And if so I should really say this is like the numbering system is, this should be A, this should be B, anyway. And this should be 1, 2, 3 of which are, then number C is if two tableaux are the same, then they are counted, the same if their labels, the labels A, B are the same. If they're not, then they're distinct. Otherwise, they refer to distinct ereps. And lastly, cancel or just cancel or just like erase columns with n boxes for SUN because they're trivial. So for example, when we did SU2, that thing we found that was actually just a fundamental because I can just, get rid of that. So these are our rules. If you guys give me like a couple of more minutes, we can do an example. No? Yes, no? Shall we do an example? This is again taken from Jones. Any mistake is because of him. I'm just kidding. And some of the stuff we have done before, like for example, you can work those out as well. And right, so example. So for SU3, we want to figure out what this is. So first we do is that we say, okay, this is going to be A, this is going to be A, this is going to be B. So then what I do is that I take first A and I add on to my first tableau in all the ways that is possible and legal. So the tableau has to be, each tableau has to be legal, but also there is the number of each box. I can associate a number NA, and that number has to be greater than or equal to NB. But so far, I'm not really messing with B, so I don't have to worry about it at this stage. So then the next step, I take the next A, and I have now 4 boxes here. And I have okay, sorry. Okay, I'm not going to organize in this way. I'm going to organize it in a different way. So first, what I'm going to draw is that I'm going to work out how, in the next step, how the diagrams that this guy gives. So I can take this A and add it here, or I can take this A and add it here. Or I can take this A and add it here. And then outside we have just B. And now I look at what are the stuff I can get from this guy. From this guy I can get these are the only two things I can get from this guy. Times B. And then the last guy is I have A and this thing. And then I can add this thing. But I cannot add A below this because that would give me 4 boxes. That's not allowed for SU3. And then the next step is to multiply these out. And you multiply when these out, because now we have to worry about the different numbers NA and NB for each of these boxes. Some of those things will be disallowed. So, so for example, if I now take B and put it, if I take B and I put it here, then oh yeah. So from the first one, I should be getting so I should be getting this and this. But if I now say I want to put the B here, so I have, say, A, this thing, and then B here. That should not be allowed. Sorry?
According to your definition, it should be exactly that.
Yeah, it should be allowed, right? According to my definition. But my notes say.
I don't think either of them should be allowed.
The box with the right quote.
The second one should definitely not be allowed.
Huh?
The second one should be allowed, right?
No, because the middle box with the A in it has a B to the right of it, which is so NB is 1, but it has no A.
Right. That's why, yeah. Thanks, yeah.
So neither of them are allowed.
So this one is not allowed because it has no A's on the right and one B on the right.
I don't.
So the value for NA is less than the value of NB. But for this thing, yeah, but for this thing, So how do we assign NA? Sorry, the way we assign NA, we count the number of A's above and right of it. So here and is or, I mean. So over here, if I look at this, it has 2 A's above, like, you know, it cannot be below. So this box will have NA equals to 2, which is greater than what the NB value is. So this is allowed, whereas this would not be allowed because this has because this box has value, NA value is 0, NB value is 1. Okay. Yeah. So then we get from the second term. Okay, so the other terms that you should be getting is this. I think I skipped a step, and which I okay, I see, right. So yeah, this is what's creating the confusion, is that this guy and this guy are the same tensor, and this guy and this guy are the same guys, and this thing and this thing are the same. So so there should be an intermediate step here where I write this tensor plus this tensor plus this tensor plus this tensor. So there's a bunch of terms which, you know, they will be, and so then I'm multiplying. So let's just do that. So I'll be done in a minute. So we are multiplying this plus this this, right, and that with B, and if you now use the rules, then you get AAB plus B AA, and then from this guy you get AAB, right, and here you get AAB, and another one which almost looks the same, but is now ABA and AAB. So because we are doing SU3, anything which has 3 columns, we are just going to cancel that. And this is going to give me 1. So the final result is this thing is going to stay. And this will be like that. This guy also stays. And this thing is a and this thing is a different, they look the same, but they're different tensor because the labels are different. This is A, this is B, and this is 1. So this is a 27-plet. This is a decuplet. And this is it turns out, I have not confirmed this. This is also 10 star. And then these are 2 different 8s plus 1. Okay. So I think I'm going to stop there.